Good morning, geometry students. Today we're going to be learning about chords and arcs. First, refresher, what is a chord? A chord is a segment whose endpoints, right, are on the circle. So this here would be a chord. Second, a central angle. If we have the center of the circle and we draw an angle whose vertex is at that center, this here would be your central angle, something we talked a lot about. Now, we know already from past what a semicircle is. It's a half a circle or 180 degrees, named using 3 points. A minor arc is less than 180 degrees, named using 2 points, the key part. And a major arc is more than 180, and it's named using 3 points. Okay? Now, there's a bunch of theorems we're going to talk about here, and then we'll go to some examples and apply them. So the first theorem is within the circle or congruent circles, right? Congruent central angles have congruent chords. So what they're saying here is if these central angles are congruent, then these chords are congruent, right? So congruent central angles have congruent chords. Okay, that's the first theorem. Second one, within a circle or congruent circles, congruent chords have congruent arcs, meaning if this chord is congruent to this chord, right? So if KJ is congruent to BC, and these are segments, right? Then we can conclude that this arc is congruent to this arc. So we could basically conclude that arc KJ would be congruent to arc BC. Okay. The next one, congruent arcs have congruent central angles. So using the last two theorems, right, and combining them, what they're basically saying is if this arc is congruent to this arc, excuse me, then this central angle is congruent to this central angle. Okay, so congruent arcs have congruent central angles. And you could basically work backwards from that and say congruent arcs have congruent chords, then have congruent central angles. Okay, so next, within a circle or in congruent circles, chords equidistant from the center are congruent. So now, anytime we talk about equidistant, if I'm going from the center to a segment, I need to have a right angle at the intersection of the two segments. Okay, now what they're saying here is if this chord, right, if KJ and BC are equidistant, meaning these segments are congruent, then we can go ahead and say the chords are congruent. Next one, congruent chords, right, are equidistant from the center. So now they're telling us these chords are congruent. So now they're giving us KJ is congruent to BC. Therefore, we know that these distances from the center will be equal also. And the next one. In a circle, a diameter that is perpendicular to a chord bisects the chord and its arcs. So if we see this diameter is perpendicular, so if we get right angles anywhere here, right, then we know this segment is congruent to this segment, and then we know this arc would also be congruent to this arc. Okay, these are all theorems we have to pay attention to when we're doing the examples. Next one, in a circle, the diameter that bisects a chord, right, is perpendicular to the chord. So if we know what they're basically telling us, they're giving us BD is congruent to CD. Now what we do is we conclude, right, that AE is perpendicular to BC. So we can conclude that there are right angles here. So in this one, in a circle, the perpendicular bisector of a chord contains the center of the circle. Now, if we know this BD is congruent to CD, and we know this is a right angle, right? But we don't know that this is the diameter. We can basically conclude that AE is the diameter from that given information. Okay? Now, what I would like you to do is go ahead, take a minute or two to try the examples applying these theorems, and then come back and watch the rest of the video. All right, let's go through some of these examples now. First one, if you're given circle O is congruent to circle P, right? And you're also given that BC, you're told BC is congruent to DF, what can we conclude? Well, we can conclude a couple of things, right? One, we can conclude that the central angles are congruent. Because remember, if chords are congruent, central angles are congruent. So angle BOC is congruent to angle DPF. And what else can we conclude? Well, if chords are congruent, then we know the arcs are congruent. So arc BC is congruent to arc DF. Okay. Next example. Find the value of A in the circle. Well, A in this case is a chord, right? Now, if we look at this, the distance from the center, you see how I get this right angle here? Since these distances are both 9 units long, what I know is these two chords are congruent. And if that's the case, if PQ is 12.5, QR is 12.5, now we could say PR is equal to 25 units, and that since they are congruent, A would have to be 25 units. Okay. Now looking at this example, it says find the value of X in the circle. Well, what theorem are we using here? Well, right away you should notice that this chord is 36 units long. This chord is 36 units long. Therefore, when I look at these distances, and I know their distances from the center because they are perpendicular to those chords, I can conclude that X is 16 units long because congruent chords, right, are equidistant from the center. All right, and that is the theorem we use. Okay, move along. Find each missing length to the nearest tenth. Well, in this case, right, when we look at this segment goes from the center perpendicular to here. Now, if you're perpendicular to here, since it could technically form a radius slash diameter, what we can conclude from this is that if this segment is perpendicular here, that ln would be congruent to nm. So this here would be 7 units long. Well, what does that form here? It forms a right angle. And what could I use to form to find the length of the hypotenuse of a right triangle? Pythagorean theorem. So 3 squared plus 7 squared equals the radius squared. So we get 9 plus 49 equals the radius squared. So the radius would be the square root of 58. All right. Now, when you put that in your calculator, the square root of 58, you get it's about, the radius of this circle would be about 7.6 centimeters long. All right. So in this example, it says find the radius of circle O and the measure of arc AB. All right. Now segment AB, right, this whole segment they're telling you is 6 units long. Now this is a little tricky here. First off, the radius. We know right away that if I draw this radius in, what I've constructed here is a right triangle. And this side is 3 units long because I know this is cut, AB is cut in half by this distance here. Okay, so I know to find the radius squared is equal to, I'm going to go ahead and use Pythagorean theorem, 3 squared plus 6 squared. So the radius is going to be the square root of 9 plus 36 is 45. Okay, now we could simplify that to 3 root 5. Or you can take it down to a decimal. But the bigger question is, how do we find the central angle or the measure of the arc? Okay. To find it, right? And I'm just going to basically talk about it because I want to get through the rest of the examples. We could use trig, which we would use tangent, right? We can say the tangent, right, of x is equal to the opposite 3 over hypotenuse 6. And the measure of this angle here, using trig, remember we use the inverse. Inverse tangent, 3 divided by 6, and you'll end up getting 26.56. So we'll say is approximately 27 degrees. And if that angle is 27 degrees, right? If I draw this other one in, that's going to be 27 degrees. And if the central angle is 54, then we could say this arc is congruent to the central angle, and arc AB would have a measure of approximately 54 degrees. Okay, the tough part about this next problem, all right, is being able to read it and know how to draw it in the diagram. So P and Q are points on circle O. The distance from O to PQ is 15. So P and Q, here's P, here's Q, right? That's that. And the distance from O, which is the center of the circle, this distance, create that right angle, right, is 15 inches. So that's 15. And PQ is 16, right? Find the radius of the circle. Well, if I draw this radius in, remember if PQ is 16, right? This here is going to be 8 and 8. And if I look, 8, 15, 17 is a triple. So the radius would be 17 units long. Now I'm going to be running out of time here. But if I'm going to find this problem here, okay, the length of the chord, what you guys have to know is you have to find the length of this segment here using Pythagorean theorem. So if I say, I'm going to call this y squared plus 4 squared equals 6.8 squared. Now, that's going to give me 6.8 squared minus 16. It's going to give you 30.24, right? So y squared equals 30.24, square root of that, right? But what you have to do is double that to get x. X is equal